Hi everyone. So queuing theory में ना basically what we are trying to learn, it's all about you know the probability of it's basically the study of queue. Like you go to bank or you go to ATMs, you'll find queues everywhere. So how long, like how people arrive, how people are serviced, and how long like it takes to clear the queue and all those kind of things. That is basically something which you are going to learn in this uh, basically this particular chapter. Yeah. And what's the utilization ratio of the servers? So I'll just take you through briefly. I'll take you through, and then we'll solve a question, and that's it. So the components of the queuing process. So basically, first thing is, so there are basically three major components. The calling population, I mean the people who are coming to the queue, coming to the system and standing in the queue. And then you have the queue, and then there is one server where people are getting serviced, and that's it. So we need to learn about the arrival process and the queue discipline and the service process. So arrival process are assumed to be the way people are arriving at the. For example, there's a bank and people are going to the branch to for withdraw cash or to do some activity. So we assume that the arrival process is often it's a Poisson distribution. In the real world, it's quite well established. So we won't debate on that. So it's a Poisson distribution that you have to remember. And then calling population is nothing but either it's a finite population that is coming to the system or an infinite population. In case of bank, we could say it's an infinite population because a lot of people are there. And the number is, like greater than 40, we usually go for a infinite population. So just forget about that. So the important things that I'll highlight here, that's basically arrival rate. The rate at which people are arriving, number of customers arriving in a per particular time period. Ignore these things and then come to the service process, the way they are getting serviced. So yeah, here comes service rate. So service rate is basically the number of customers getting served. Imagine you go to SP and there are four kiosks or four different people sitting there. So there are four different servers and number of customers getting served per time period, let's say for 1 hour. So that is basically your service rate, and that always follows a exponential distribution, exponential service distribution. So Sir said on like in this thing, that service E stands for exponential, like that. And then your arrival is always Poisson. You just remember these two things. uh, yeah. So you have single queue where you have to go through only one queue, and then there are multiple queues because there are multiple servers. In our exam, will mostly deal with single queue, multiple queues are not there. So next we come to the standard, yeah. So this LIFO and FIFO, the queue discipline, as in how people are getting serviced. If LIFO, FIFO, right? The first person, the person who comes first gets service first. That's FIFO. And LIFO and random order are it's self-explanatory. I'm not gonna explain that. So, and system capacity is how many people can be serviced. So it's finite or infinite. That's it. So this is the important part. We'll come to this notation. So A slash B slash C. So the A basically is the arrival pattern, which it's always exponential. Sorry, it's always Poisson. Okay. And then B is the service pattern. We know that it's always exponential. And C is basically the number of servers available. How many desks are there in the bank? Uh, it can be one, two, or many, right? In our course, we are mostly dealing with one server. And was the system capacity, is it finite or infinite? And then was the queue discipline, first in, first out, or random, or the person who came last is getting service first? So we call it as MM1, that is aims for arrival and aim for service, and one stands for only single channel server, And infinite stands for the infinite system capacity, and FCS is first come first serve. So this is it. And then you have, so these assumptions are basic. So you have certain formulas using which you will be solving the numericals. So in question paper, you will get a 5 mark question, and that's it. So I okay, I'll just give you a small brief, and all the remaining formulas are actually self-explanatory. You just have to read the question and then use the suitable formula. The probability of no customers in the system. I mean the pro. So, yeah, just to give you a context, imagine when you are designing a system, you are designing a bank. So how will you design the system? Every time you will design it such a way that there is the queues are getting cleared. I mean, like if 10 people are arriving, then you'll at least make sure that you can service more than 10 people, right? So 10 is your lambda, and this service rate is your mu. So you'll at least make sure that you can service more number of people than arriving, right? So in that case, the system utilization, if I have to calculate this value, the system utilization will be lambda by mu, because you have built a capacity of 11 but only 10 people are coming. So your system utilization will be 10 by 11. So that is basically your traffic intensity, how many people are there. And if you subtract that from 1, so that is 1 minus rho, that will give you probability of no customers when your system utilization is basically 0, right? So if these two things are clear, then we'll move to the further formulas ki probability of n customers in the system. And so uh, all these things can be derived, but there is no point in doing that because we are getting the formulas anyway. And so just a clarification that when you talk about system, so check formula 4 and 5, this might look similar, but when you talk about system, so system is basically the queue plus the one person who is getting service right now. So that's why one person in service. So that's why you can see probability that there are more than n customers in the queue, and probability that there are n customers in the system. So n customers in the queue means n plus 1 customers in the system, because n people are standing in the queue and one guy is getting serviced. So if you substitute n plus 1 here, then it directly I mean like so probability of n customers in the queue is this, or probability of n plus 1 customers in the system will be n plus 1, that is n plus 2. So this is same as this. So this is the only thing that you need to remember: system equal to q plus 1% in service. And other formulas are purely self-explanatory. I'll not explain that. So we'll go back to question. So yeah, so if you see in the question paper, yeah, so this is basically a question from the previous year paper. So what they have told, that I have written down all the like parameters. They've said that Shreya is organizing a party, basically hostel day celebration, and people are arriving at the rate of 10 per hour. So the arrival rate lambda, that is basically 10 per hour. Okay, lambda, we know lambda is 10. And then what is the next information that they have given, that she has a single counter that can serve at 5 minutes per person, so each person takes 5 minutes. So if I have to calculate the service rate, which is mu, so per hour service rate will be 60 minute divided by 5 minute, because each person takes 5 minutes. So within 1 hour she can service 12 persons per hour. So the service rate is mu, right? So I know arrival rate, that is 10 persons, and service rate is 12 persons. So then she is asking so they are asking the next question, that is what is the utilization of the server. So right now I have told that your utilization is nothing but your arrival rate by service rate. We usually keep service rate high, right? Because that's how we design our system. So utilization, that is rho equal to lambda by mu. You can see that in the formula also. If you go here, then yeah, the first formula, system utilization or traffic intensity. So that is basically your utilization of the server. So that is lambda by or mu. It's nothing but 10 by 12 or 83%. Okay. In the second question that they have written, what is the probability of no queue in the system? So no queue means the system is not being utilized at all. So the utilization is zero. So that is basically nothing but probability of no customer or empty system. So that is 1 minus rho, and 1 minus rho will be 1 minus 83.3, that is 16.7%. And the last question there that they are saying, if we assume that arrival does not join in line, assuming that arrival does not join the line if more than 10 people are there in the system. If more than 10 people are there in the party, the people won't join the party. So what is the probability that people are not joining the party or not joining the line? Okay. So this is basically, we go back to the same question, probability that there are more than 10 people in the system. Okay. So we know the formula, that is rho to the power n plus 1. So probability that there are more than 10 people in the system. So we can simply write that as rho to the power 10 plus 1 or rho to the power 11. Calculate this value, rho, and you can calculate rho to the power 11, and that will be the final answer. And that's it. And you will get questions similar to this. You just have to find the formula that fits your case. That's it, and nothing else. Yeah. Thank you.